Scuzzy redirects here. For the historic sternwheeler known by that name, see Scuzzy. Small Computer System Interface is a set of standards for physically connecting and transferring data between computers and peripheral devices. The SKUZ-ee standards define commands, protocols and electrical and optical interfaces. SKUZ-ee is most commonly used for hard disks and tape drives, but it can connect a wide range of other devices, including scanners and CD drives, although not all controllers can handle all devices. The SKUZ-ee standard defines command sets for specific peripheral device types. The presence of unknown as one of these types means that in theory it can be used as an interface to almost any device, but the standard is highly pragmatic and addressed toward commercial requirements. SKUZ-ee is an intelligent, peripheral, buffered, peer-to-peer interface. It hides the complexity of physical format. Every device attaches to the SKUZ-ee bus in a similar manner. Up to 8 or 16 devices can be attached to a single bus. There can be any number of hosts and peripheral devices, but there should be at least one host. SKUZ-ee uses handshake signals between devices. SKUZ-ee1, SKUZ-ee2 have the option of parity error checking. Starting with SKUZ-ee U160, all commands and data are error-checked by a 32 Costa Rican colons checksum. The SKUZ-ee protocol defines communication from host to host, host to a peripheral device to a peripheral device. However, most peripheral devices are exclusively SKUZ-ee targets, incapable of acting as SKUZ-ee init or unable to initiate SKUZ-ee transactions themselves. Therefore, peripheral-to-peripheral communications are uncommon, but possible in most SKUZ-ee applications. The Symbio's Logic 53C810 chip is an example of a PCI host interface that can act as a SKUZ-ee target. History: SKUZ-ee was derived from SASI, the Shugart Associates System Interface, developed c. 1978 and publicly disclosed in 1981. A SKUZ-ee controller provided a bridge between a hard disk drive's low-level interface and a host computer, which needed to read blocks of data. SKUZ-ee controller boards were typically the size of a hard disk drive and were usually physically mounted to the drive's chassis. SKUZ-ee, which was used in mini and early microcomputers, defined the interface as using a 50-pin flat ribbon connector, which was adopted as the SKUZ-ee1 connector. SKUZ-ee is a fully compliant subset of SKUZ-ee1, so that many, if not all, of the then existing SKUZ-ee controllers were SKUZ-ee1 compatible. Larry Buescher is considered to be the father of SKUZ-ee and SKUZ-ee due to his pioneering work first at Shugart Associates and then at Attached Scsi. Until at least February 1982, ANSI developed the specification as SKUZ-ee, and Shugart Associates System Interface. However, the committee documenting the standard would not allow it to be named after a company. Almost a full day was devoted to agreeing to name the standard Small Computer System Interface, which Buescher intended to be pronounced SKUZ-ee, but Ian Dielsdale Allen pronounced the new acronym as SKUZzy, and that stuck. A number of companies such as NCR Corporation, Adapt and Optimum were early supporters of the SKUZ-ee standard. The NCR facility in Wichita, Kansas is widely thought to have developed the industry's first SKUZ-ee chip. It worked the first time. The small part in SKUZ-ee is historical. Since the mid-1990s, SKUZ-ee has been available on even the largest of computer systems. Since its standardization in 1986, SKUZ-ee has been commonly used in the Amiga, Apple Macintosh and Sun Microsystems computer lines and PC server systems. Apple started using parallel ATA for its low-end machines with the Macintosh Quadra 630 in 1994, and added it to its high-end desktop starting with the Power Macintosh G3 in 1997. Apple dropped onboard SKUZ-ee completely with the Power Mac G3 in 1999, while still offering a PCI controller card as an option on up to the Power Macintosh G4 models. Sun has switched its lower-end range to serial ATA. Commodore included a SKUZ-ee interface on the Amiga 3000-3000T systems, and it was an add-on to previous Amiga 500/2000 models. starting with the Amiga 6004000 systems. Commodore switched to the IDE interface. SCSI has never been popular in the low-priced IBM PC world, owing to the lower cost and adequate performance of ATA hard disk standard. However, SCSI drives and even SCSI RAIDs became common in PC workstations for video or audio production. Recent versions of SCSI Euro serial storage architecture, SCSI over Fibre Channel protocol, serial attached SCSI, automation drive interface a transport protocol, and USB attached SCSI Euro break from the traditional parallel SCSI standards and perform data transfer via serial communications. Although much of the documentation of SCSI talks about the parallel interface, most contemporary development effort is on serial SCSI. Serial SCSI has a number of advantages over parallel SCSI, faster data rates, hot swapping, and improved fault isolation. The primary reason for the shift to serial interfaces is the clock skew issue of high-speed parallel interfaces, which makes the faster variants of parallel SCSI susceptible to problems caused by cabling and termination. SKUZ-ee preserves the basic SCSI paradigm, especially the command set, almost unchanged, through embedding of SCSI 3 over TCP/IP. SCSI is popular on high-performance workstations and servers. RAIDs on servers have almost always used SCSI hard disks, though a number of manufacturers now offer SATA-based RAID systems as a cheaper option. Instead of SCSI, desktop computers and notebooks more typically use ATA interfaces for internal hard disk drives, and USB, eSATA, and FireWire connections for external devices. As of 2012, SCSI interfaces had become impossible to find for laptop computers. AdaptCAD years before produced PCM-CIA SCSI interfaces, but when PCM-CIA was superseded by the Express card, AdaptCAD discontinued their PCM-CIA line without supporting Express card. Ratek produced USB and FireWire to SCSI adapters, but ceased production when the integrated circuits required were discontinued. Drivers for existing PCM-CIA interfaces were not produced for newer operating systems. Interfaces. SCSI is available in a variety of interfaces. The first, still very common, was parallel SCSI, which uses a parallel bus design. As of 2008, SPI is being replaced by serial attached SCSI, which uses a serial design but retains other aspects of the technology. Many other interfaces which do not rely on complete SCSI standards still implement the SCSI command protocol. Others drop physical implementation entirely while retaining the SCSI architectural model. SKUZ-ee, for example, uses TCP/IP as a transport mechanism. SCSI interfaces have often been included on computers from various manufacturers for use under Microsoft Windows, Mac OS, Unix, Commodore Amiga and Linux operating systems, either implemented on the motherboard or by the means of plug-in adapters. With the advent of SAS and SATA drives, provision for SCSI on motherboards is being discontinued. A few companies still market SCSI interfaces for motherboards supporting PCIe and PCIX. Parallel SCSI. Development of the SCSI parallel interface ended with the publication of SPI5 in 2003. All of the versions of the interface are defined in SPI5, except for high voltage differential, which is in SPI2. All other versions of SPI have been withdrawn. The SCSI specifications include several synchronous transfer modes for the parallel cable, but also an asynchronous mode. The asynchronous mode is a classic request-acknowledge protocol. It allows systems with a slow bus or simple systems to also use SCSI devices. More frequently, the faster synchronous modes are used. Other SCSI interfaces, cabling. SCSI parallel interface. Internal parallel SCSI cables are usually ribbons, with 2 or more 50 euro, 68 euro, or 80 euro pin connectors attached. External cables are typically shielded, with 50 euro, or 68 euro pin connectors at each end, depending upon the specific SCSI bus width supported. The 80 Euro pin single connector attachment is typically used for hot pluggable devices. Fibre channel. Fibre channel can be used to transport SKSI information units, as defined by the Fibre Channel protocol for SKSI. These connections are hot pluggable and are usually implemented with optical fiber. Serial attached SKSI. Serial attached SKSI uses a modified serial ATA data and power cable. ๊skʌzi. ๊skʌzi usually uses Ethernet connectors and cables as its physical transport, but can run over any physical transport capable of transporting IP, SIP. The SKSI Rdma protocol is a protocol that specifies how to transport SKSI commands over a reliable Rdma connection. This protocol can run over any Rdma-capable physical transport, for example InfiniBand or Ethernet when using ROCE or I-Warp. USB-attached SKSI. USB-attached SKSI allows SKSI devices to use the Universal Serial Bus. Automation Drive Interface. The Automation Drive Interface, a transport protocol, is used to connect removable media devices, such as tape drives, with the controllers of the libraries in which they are installed. The ADI standard specifies the use of RS-422 for the physical connections. The second-generation ADT2 standard defines IADT, use of the ADT protocol over IP connections, such as over Ethernet. The Automation Drive Interface command standards define SKSI commands for these installations. SKSI Command Protocol. In addition to many different hardware implementations, the SKSI standards also include an extensive set of command definitions. The SKSI command architecture was originally defined for parallel SKSI buses but has been carried forward with minimal change for use with ๊skʌzi and serial SKSI. Other technologies which use the SKSI command set include the ATA packet interface, USB mass storage class and FireWire SBP2. In SKSI terminology, communication takes place between an initiator and a target. The initiator sends a command to the target, which then responds. SKSI commands are sent in a command descriptor block. The CDB consists of a 1-byte operation code followed by 5 or more bytes containing command-specific parameters. At the end of the command sequence, the target returns a status code byte, such as 0 hour for success, 2 hours for an error, or 8 hours for busy. When the target returns a check condition in response to a command, the initiator usually then issues a SKSI request sense command in order to obtain a key code qualifier from the target. The check condition and request send sequence involves a special SKSI protocol called a contingent allegiance condition. There are 4 categories of SKSI commands, N, W, R, and B. There are about 60 different SKSI commands in total, with the most commonly used being, test unit ready, queries device to see if it is ready for data transfers. Inquiry, returns basic device information. Request sense, returns any error codes from the previous command that returned an error status. Send diagnostic and receive diagnostic results, runs a simple self-test, or a specialized test defined in a diagnostic page. Start-stop unit, spins disks up and down, or loads-unloads media. Read capacity, returns storage capacity. Format unit, prepares a storage medium for use. In a disk, a low-level format will occur. Some tape drives will erase the tape in response to this command. Read, reads data from a device. Write, writes data to a device. Log sense, returns current information from log pages. Mode sense, returns current device parameters from mode pages. Mode select, sets device parameters in a mode page. Each device on the SKSI bus is assigned a unique SKSI identification number or ID. Devices may encompass multiple logical units, which are addressed by logical unit number. Simple devices have just one LUN, more complex devices may have multiple LUNs. A direct access storage device consists of a number of logical blocks, addressed by logical block address. A typical LBA equates to 512 bytes of storage. The usage of LBAs has evolved over time, and so 4 different command variants are provided for reading and writing data. The read, 6, and write, 6, commands contain a 21-bit LBA address. The read, 10, read, 12, read long, write, 10, write, 12, and write long commands all contain a 32-bit LBA address plus various other parameter options. The capacity of a sequential access device is not specified because it depends, amongst other things, on the length of the tape, which is not identified in a machine-readable way. Read and write operations on a sequential access device begin at the current tape position, not at a specific LBA. The block size on sequential access devices can either be fixed or variable, depending on the specific device. Tape devices such as half-inch 9-track tape, DDS, exabyte, etc., support variable block sizes. Device identification: on a parallel SKUZ-ee bus, a device is identified by a SKUZ-ee ID, which is a number in the range 0-7 on a narrow bus and in the range 0-15 on a wide bus. On earlier models, a physical jumper or switch controls the SKUZ-ee ID of the initiator. On modern host adapters, doing I/O to the adapter sets the SKUZ-ee ID. For example, the adapter often contains a BIOS program that runs when the computer boots up, and that program has menus that let the operator choose the SKUZ-ee ID of the host adapter. Alternatively, the host adapter may come with software that must be installed on the host computer to configure the SKUZ-ee ID. The traditional SKUZ-ee ID for a host adapter is 7, as that ID has the highest priority during bus arbitration. The SKUZ-ee ID of a device in a drive enclosure that has a backplane is set either by jumpers or by the slot in the enclosure the device is installed into, depending on the model of the enclosure. In the latter case, each slot on the enclosure's backplane delivers control signals to the drive to select a unique SKUZ-ee ID. A SKUZ-ee enclosure without a backplane often has a switch for each drive to choose the drive's SKUZ-ee ID. The enclosure is packaged with connectors that must be plugged into the drive where the jumpers are typically located. The switch emulates the necessary jumpers. While there is no standard that makes this work, drive designers typically set up their jumper headers in a consistent format that matches the way that these switches implement. Note that a SKUZ-ee target device is often divided into smaller logical units. For example, a high-end disk subsystem may be a single SKUZ-ee device but contain dozens of individual disk drives, each of which is a logical unit. Further, a RAID array may be a single SKUZ-ee device, but may contain many logical units, each of which is a virtual disk, a stripe set or mirror set constructed from portions of real disk drives. The SKUZ-ee ID, WWN, etc. in this case identifies the whole subsystem, and a second number, the logical unit number, identifies a disk device within the subsystem. It is quite common, though incorrect, to refer to the logical unit itself as a LUN. Accordingly, the actual LUN may be called a LUN number, or LUNID. Setting the bootable hard disk to SKUZ-ee ID 0 is an accepted IT community recommendation. SKUZ-ee ID 2 is usually set aside for the floppy disk drive, while SKUZ-ee ID 3 is typically for a CD-ROM drive. In modern SKUZ-ee transport protocols, there is an automated process for the discovery of the IDs. The SSA initiator walks the loop to determine what devices are connected and then assigns each one a 7-bit hop count value. Fibre Channel arbitrated loop initiators use the LIP to interrogate each device port for its WWN. For SKUZ-ee, because of the unlimited scope of the network, the process is quite complicated. These discovery processes occur at power on initialization time and also if the bus topology changes later, for example if an extra device is added. Device type. While all SKUZ-ee controllers can work with read-write storage devices, that is disk and tape, some will not work with some other device types. Older controllers are likely to be more limited, sometimes by their driver software, and more device types were added as SKUZ-ee evolved. Even CD-ROMs are not handled by all controllers. Device type is a 5-bit field reported by a SKUZ-ee inquiry command. Defined SKUZ-ee peripheral device types include, in addition to many varieties of storage device, printer, scanner, communications device, and a catch-all processor type for devices not otherwise listed. SKUZ-ee enclosure services. In larger SKUZ-ee servers, the disk drive devices are housed in an intelligent enclosure that supports SKUZ-ee enclosure services. The initiator can communicate with the enclosure using a specialized set of SKUZ-ee commands to access power, cooling, and other non-data characteristics. See also, Fibre Channel, List of device bandwidths, Parallel SKUZ-ee, Serial Attached Scsi, References. Bibliography. External links.